that is related to time independent Schrodinger equation, sometimes time dependent Schrodinger equation. Okay. So now minus h bar square by 2m, okay, d square psi by dx square, okay, plus v of x into psi is equal to E into psi. E is the energy. Am I right? Now what I do is I am going to modify this one. D square psi by dx square, okay, speak up, is equal to, can I write 2m by h bar square. Check this out. V of x minus E or E minus V of x minus E? V of x minus E, okay, V of x minus E multiplied with psi again. I'll just keep this one as one equation. Okay. I'll just keep this one as one equation. Okay. The question will be like this. Okay. Speak up. Given psi of x, they'll give psi of x. Speak up. Find V of x and E. They will give the wave function. I mean, which is, they will say that it's a solution of time independent Schrodinger equation. Find V of x and E. Then what would you do? You take this wave function, okay, you take its second derivative, psi given, okay, divided by dx square. Speak up. That second derivative can be written like this: some function of x plus some constant into again the wave function. It can be written like this. It can be written like this. When you take second derivative, if you try to separate the wave function from the second derivative, one function, one constant will remain. I will say this is second equation. Now compare first and second equation. What would you say? This any functionality part, that's your potential. Any constant, that's your energy. Is that okay? I mean, the idea is this V of x is purely what you call variable part. In this one, this is a purely variable part. There should not be any constant part. If there is any constant part, you take it to right hand side. You keep it along with the energy. That is the basic idea. That's the basic assumption that I made. Okay, speaker. Ground state, apart from normalization, pick up ground state, apart from normalization constant is not required to do this. You're taking psi again. You keep psi, I mean, normalization constant inside psi. That's it. It doesn't matter. Okay, you are taking this psi outside again. Okay, speaker. Apart from normalization constant of a particle of unit mass moving in one-dimensional potential, okay, speak up, is e power psi of x, that's equal to, speak up, e power minus x square by 2, okay, into cos hyperbolic of root 2x. Root 2x. The potential is v of x in the suitable units, okay, so that h bar equal to 1. H bar equal to 1, m equal to 1. So that this will be very simple. Mass equal to 1, h bar equal to 1. Okay, speak up to an additive constant. Okay, speak up. You can leave the additive constant also. Up to an additive constant. Okay, speak up. What is the potential? What you do? You slowly find its first derivative, psi of x by dx. Okay, try to separate psi here itself. Okay, that's better. Okay, then take d square psi of x by dx square. Okay, then that can be written as, I hope, some f of x plus some constant into psi of x again. Check that out. It can be written because this cos hyperbolic, exponential, its derivative will contain the same function. Am I right? I mean, e power x square by 2 after taking derivative, maybe minus 2 x by 2 may come, but still e power minus x square by 2 will remain, isn't it? Cos hyperbolic after taking couple of derivative, you will get again cos hyperbolic, isn't it? That's why try to write like this and find the appropriate answer. Is that okay? I can't think. In place of root 2, if I had some lambda, if I put that lambda, if that lambda is 0, then it will be harmonic oscillator kind of thing. Am I right? Then it should be either this one or this one. I mean, I'm trying to eliminate option, but I don't think they are expecting you to do this one. I feel like that. Now, what I'm saying is, okay, in the exam hall, you will not be having all lengthy problem. Okay, most of the problem you have to see the way that he is expecting, and it will be quickly solved. One or two problem will always be there in all exam, which is taking more than 10-minute time.
Because I knew that if I do like I will double derivative, I will get the answer.
Mm-hmm.
But then I just kept going and it will.
I mean, that's what I'm saying. In exam, in the full length exam, okay, choosing the question is also part of the competition. I mean, you should not hit your head with stone, okay, at in the exam hall. Okay, right now you have to what you call make your head strong. Okay, speak up. But in the exam hall, choosing the question is also part of the competition. You know how much time it takes. Keep it later. If suppose all known questions are done, then you choose the question last 15 minutes. Like that you need to handle. But I mean, I'm expecting you should do slightly faster, neatly, without mistake. Anyway, it is required. But remember, I mean, you don't have to worry. I mean, maybe in the test I kept all problem, right, from all various exams. Some problem may be very lengthy. Some problem may be very easy. Okay, exam will be mixture of them. Okay, you don't have to worry. Okay, but I feel at least 10 minutes. Okay, not more than 10 minutes. Okay, speak up. Yeah, but I mean, what I was thinking, are you getting my point? Suppose if this root 2 was lambda, if lambda equal to 0, this is harmonic oscillator wave function, isn't it? Then cot hyperbolic 0 is infinity, I think, am I right? Isn't it? Tan hyperbolic 0 is 0. This is infinity. I mean, I can remove this one. I mean, I know that it cannot be x square. It should have one more factor. I can remove this one. Among these two is but the tan function having a lot of discontinuity. Am I right? Speak up. This tan function, I mean, at minus pi by 2 plus pi by, but tan hyperbolic is a smooth function. Speak up. Like that, I mean, you can do, but I mean, I will do eliminate option if it is feasible. Okay, I mean, you eliminate option if it is feasible. Okay, here I think it is feasible. You know that it's not tan because it is having many discontinuities. Okay, speak up. But I mean, you after solving problem in the ideal method, you sit and think, what else I can do? That's what required for the exam. Is that okay? Actually, whenever this kind of problem is there, you better to apply whatever you know. What is that harmonic oscillator you know? Am I right? So where beta is, when beta is 2, this will be also 2. Am I right? Lambda is also 2. But that won't work here. Check this out. All options are like this. If beta equal to 2, lambda is also 2. I try to apply harmonic oscillator, which I know Gaussian is one of the wave function, e power minus x square. That won't work. And one more thing, he is expecting something else. Okay, this is the potential only for large x value. This is the wave function, isn't it? If wave function is given, we can find the potential. We had one idea, am I right? Now he is not asking potential. He is asking that beta lambda relations, isn't it? That's why what you have to do here is, while doing the problem, you have to make that approximation. You take its second derivative. Okay, I mean d square psi by dx square plus v of x into psi is equal to e into psi. Okay, speak up. Plus e into psi. Okay. Now, when you take second derivative, when you write the step, am I right? So in that step, you make this approximation. Let x be very large. For large x, what happens? This v of x replaced by kx power beta. What do you say? Can you quickly find the second derivative of this one? d psi by dx. Okay, I mean psi of x is equal to e power minus x power lambda, e power minus x power lambda, okay, into minus lambda x power lambda minus 1. Am I right? Is that okay? Hmm? So d square psi by dx square, that's equal to, I better to write in terms of psi again. Am I right? That was my idea. Hmm? Minus lambda x power lambda minus 1 into psi again. What do you say? Hmm? Speak up. So then d square psi by dx square, that's equal to, I'll minus lambda, I'll take its derivative. Okay, lambda minus 1 x power lambda minus 2 psi as it is. Okay, speak up, plus minus lambda x power lambda minus 1. Okay, d psi by dx, isn't it? D psi by dx is itself minus lambda x power lambda minus 1 psi. Is that okay? What do you say? Hmm? So this is minus lambda into lambda minus 1 x power lambda minus 2 psi plus lambda square x power 2 lambda minus 2 psi. Am I right? Speak up. That's your second derivative. Minus h bar square by 2m. Okay. Into second derivative. This whole thing. Anything can be taken common. Psi can be taken common. Hmm? Psi can be taken common.
X power lambda.
Wait a second. Minus lambda into lambda minus 1 x power lambda minus 2 plus lambda square x power 2 lambda minus 2. Okay, into psi. Am I right? Is that okay? Minus h bar square by 2m second derivative. Okay, plus v of x into psi, that's equal to e into psi. Okay. Now, when x is very large, what will happen to e power minus x power lambda for large positive value of x? Zero. If it becomes zero, you have to zero equal to zero. The equation turns out to be zero equal to zero. How do you handle? How do you write e power lambda plus lambda minus 2? Okay. E power lambda minus 2 can be taken common. Am I right? Speak up. Hmm? So minus h bar square by 2m. Okay. So what this one can be written? 1 lambda minus lambda square. Hmm? So plus lambda square x power lambda x power lambda minus 2 psi plus v of x psi, that's equal to e into psi. I mean, for large x, v of x is equal to, what is that? For large x, v of x is nearly equal to kx power beta. Now he has given that one, means for large positive x values. Okay, this should be this one. That means we need to apply that one. Okay, in our step. Okay, otherwise, what is the role of this information? Isn't it? You need to apply that one. But when I take that approximation, check how you apply that approximation when x is very large value. V of x nearly equal to, what is this one? Kx power beta. So this is my second derivative. Okay, lambda minus lambda square. Okay, plus lambda square x power lambda. Okay, multiplied with x power lambda minus 2 psi. This is second derivative. Am I right? That's equal to 2m by h bar square v of x psi minus 2m e by h bar square psi. Okay, speak up. Now this should go with this one. This should be equal to this one. What is this one now? 0. Ground state energy, nearly 0 or something. Okay, speak up. Now again make that approximation. Okay, speak up for large x value. Okay. Now, yeah, I mean, we found v of x in this method only. Am I right? Isn't it? We found v of x in this method only. Okay, you write v of x. Okay, what is v? I mean, what is 2m by h bar square into v of x? Pick up. That's equal to lambda minus lambda square. Okay, plus lambda square x power lambda into x power lambda minus 2. This is v of x, isn't it? According to our old idea, we found v of x here. That's why I just compared these two. So my v of x is, okay, v of x is h bar square by 2m into this whole thing. Now you do that approximation. Again, this part is neglected. Lambda minus lambda square plus lambda square x power lambda, okay, multiplied with x power lambda minus 2. Okay, so k x power beta for large x value, this can be neglected. Okay, h bar square by 2m x power 2 lambda minus 2. That works. This idea works. I h bar dou psi by dou t, that's equal to minus h bar square by 2m dou square psi by dou x square plus v into psi. Did he mention any problem in the first chapter like this? Find the potential. Did he mention? No, that's not the problem. I'm asking whether any problem where potential to be found in the first chapter. Problem 1.9. 1.9. Check this out. Psi of x comma t, that's equal to, speak up, a e power minus a m x square by h bar, okay, into e power minus, speak up, a into I into t. Now look at it. If you solve problem twice, that's also better. It's our old student Durgesh. He said, I mean, he couldn't understand once. He solved 3 to 4 times, book again and again. I mean, you forgot, am I right? Speak up. This problem. How do you find v of x? You just substitute here. I think you can find v of x. What I'm saying here is, okay, after taking the derivative, if you take time derivative, something will come outside. Again, it can be written in terms of wave function. After taking second space derivative, again you can write in terms of wave function. That will be cancelled. You can solve for potential. Part B of the problem, for what potential, this is the solution of Schrodinger equation. Okay, so I h bar dou psi by dou t, that's equal to I h bar minus AIT, that will come outside, into wave function again. What is this one? H bar into A simply, sorry, why t came? Time derivative minus A into y, time derivative of this one, into exponential again. Okay, the whole thing is wave function again, isn't it? There's h bar into A into wave function. Speak up. So now, so dou psi by dou x, what is this one? This may be a bit lengthy, am I right? A into minus 2a m x by h bar into e power minus that is psi again, am I right? Speaker. Apart from this one, this whole thing is psi again. Psi again, can you check this out? dou square psi by dou x square. Now you do very proper game here. You take derivative of this one minus 2am by h bar, x derivative 1 psi as it is. Okay, speak up. So plus minus 2am x by h bar, okay, into psi derivative. What is psi derivative? That is this itself. Psi derivative. U into V formula, isn't it? I mean, this kind of mathematical skill is required now. Okay, so that is minus 2am x by h bar into psi again. Am I right? Now substitute over there. Okay, because what is this one? This one is h bar a into psi. That's your left hand side. Minus h bar square by 2m multiplied with this whole thing. Psi can be taken outside. When you multiply with this whole thing, look at here, that's equal to minus 2am by h bar, okay, plus 2am by h bar into x square. This is the whole square into x square, isn't it? Psi outside plus v of x into psi, or v of x comma t. We don't know whether it's time dependent or not, isn't it? Psi got cancelled. No more operation. We did all operations here. Okay. Now what will happen is I think this part will get cancelled. Check this out. H bar a psi, that's equal to h bar a psi plus rest of the part is 2m by h bar a square minus, I think, minus, okay, 2m by h bar. Sorry, h bar square got cancelled. Or 2m will remain 2m a square x square into psi. Check this up, plus v into psi. Okay, this got cancelled actually. What is v of x? Have you done that one? Minus 2m a, sorry, plus 2m a square x square when it comes this side. I mean, given the wave function, finding the potential. That is the problem that I am discussing here. Okay, speak up. Very simple. Very simple. I think this is more simpler than earlier one. I mean, this problem. Why? I mean, this problem derivatives may, second derivative, that may be quite lengthy to manipulate. Check this out. Okay, do it neatly. Neatness does matter. Okay, pick up. Do it neatly. If you do it neatly, definitely you will get the answer quickly. Okay, speak up.